Okay, let me see how many. I still have
16.
a lot of people missing right now, hopefully. Okay, just wait a minute for everybody. There's a chat. Okay, Oscar is here. Okay, I think we may start, and we were at last class. We left off somewhere here. We talked about the different end conditions of your column, the different formula for each of the end conditions, right? People, can you hear me?
Yeah.
Okay, so I'm going to talk about what is called slenderness ratio. Okay, let's talk about slenderness ratio. What is slenderness? Before we talk about it, for any type of column, you can see that it actually bends. So there is always a curvature. See, there is a curvature here. For any type, you can see a curvature. So for any type of column, you have a curvature, and this curvature has some radius. We call this radius as the radius of gyration of curvature, or you can say just radius of curvature. Okay, so moment of inertia is actually equal to area, cross-sectional area, times this radius of curvature. So you can actually replace this I here with this quantity. If you do that, this is your equation. And I can write this equation down just like this. PCR divided by APCR is your critical load. Remember, critical load is the load at which your column starts to buckle, and without any control, and actually it's going to any type of lateral disturbance. Lateral disturbance means this way. Any type of lateral disturbance will cause it to snap. So that is your critical load. So critical load divided by A is your critical stress. Critical stress on your beam, not beam, column. And this is pi, and you can call this ratio, it has a special name called slenderness ratio. And what is LE, people? If you recall from my last lecture, effective length. Effective length depends on the end condition. Is it a pinned, free, what type of column you have? Okay, so critical bucklings. So if you were to draw for steel, for example, stress versus slenderness ratio, just like the just what I have here. Okay, critical stress versus slenderness ratio, you will see that at somewhere around a slenderness ratio of 100. Just give me a second. Okay, so at a slenderness ratio of 100, the critical stress that you're gonna see is this value, and it is equal to the proportional limit of steel. Okay, so what does this mean? This is very important. It means that if your slenderness ratio is less than 100, the critical stress that you see is much higher than the proportional limit. Now, for any engineering structure, we consider that structure to have failed if it has reached its proportional limit or yielding limit, because in reality you cannot see proportional limit, right? Yielding is what we say, hey, proportional limit, elastic limit, and yielding, they all appear so close. We consider the yielding to be close to proportional limit. So we can say that, hey, below 100 slenderness ratio, the critical stress that you're going to be calculating is much higher. So the material is going to yield, or in other words, fail before you reach the critical load. So for a slenderness ratio of less than 100, critical load doesn't make any sense, because your calculation of critical load does not make any, or critical stress calculation does not make any sense, because it is the material property, that is the yielding stress or the proportional limit, that is going to dictate the failure. But once you start, once your proportional limit becomes greater than 100, what happens, you see, when it is greater than 100, the stress, critical stress that you see is less than the proportional limit or yielding. That means for if your column is long enough, slender enough, if the slenderness ratio is high, then your failure is dictated by the critical stress, because you are going to reach critical stress before you reach the yielding criteria. And as you know, if you are at the critical load causing critical stress, your column is going to fail by buckling. So at critical stress, it fails by buckling. Okay, so you will see that, so the load carrying capacity of steel column is determined by critical load when your ratio is greater than 100. But if it is less than 100, we are not too worried. We are going to only check that, check for yielding, and we're going to just check that, hey, the stress is not too high, it's not exceeding the yielding strength. As long as it doesn't, it's fine. But once you reach this critical slenderness ratio, that then you're more concerned about this critical stress. So that's what I'm saying over here, that critical buckling stress makes sense only when it is less than the proportional limit stress, and you will only get your critical buckling stress to be less than the proportional limit stress if your column is long, slender enough. That means when the slenderness ratio is very high. So long columns have critical stress much lower than your proportional limit, and that's why it is of concern. For long column, people mostly calculate the critical buckling stress, because that's what determines the failure criteria. Now, a lot of the time in civil engineering, you'll see they are going to deal with short column. Anything less than 50, any column with a slenderness ratio less than 50 is a short column, and they actually fail by crushing, okay, not by buckling. And for intermediate column, you have failure somewhere in between, like 50 to 100 is somewhere you can consider to be 50 to 200 slenderness ratio is intermediate, where if you have your slenderness ratio to be 100, so it is high enough to cause failure by buckling. Now, so in what direction will your column buckle? So we will soon see a problem now. So we have to keep this in mind. A column always tends to buckle in the direction that offers least resistance to bending. And you're going to see least, that means buckling will occur about the axis that yields the least moment of inertia of the cross section. So if you have a cross section like this, let me draw it. It doesn't look good. Okay, here. So this is your column. We're soon going to see another problem. So you're going to have, say this is H, say this is B, okay? Now it can buckle. The axis about which it will buckle will be determined in which direction, about which direction you have least moment of inertia. So if you're talking about this axis, your moment of inertia is going to be, so if this is say Z, and say this is say Y, for example, okay? So if you were to calculate moment of inertia about the Z axis, so it's going to be what? B H cubed by 12. Whereas if you were to calculate the moment of inertia about the Y axis, so my Y axis doesn't look good, okay. Say my Y axis is something like this. So about the Y axis, then it's going to be H times B cube by 12. Whichever will give you lowest moment of inertia, about that axis, it's going to bend. So we're going to look at a problem now. Before I move forward with the problem, is there any question you guys have regarding slenderness ratio, vertical buckling load?
No, everything's pretty good.
I'm going to give you guys some reading assignments once I finish this. This is the end of column. We're going to look at a worksheet and I'll give you guys some reading assignments on it. So let's look at the worksheet problem that I have already posted on Blackboard. Worksheet number 14. Okay, so let's look at this. This is from your book, problem 10.11. So let's look at this problem. The 5-meter long wooden column is built in at its base and stayed two cables at the top. So you have two cables basically here, one cable here, one cable here. Okay, the turnbuckles in the cables are turned until the tensile force on each cable is T. Okay, so the tensile force on each cable is T. Okay, determine the value of T that would cause the column to buckle. So let's analyze this problem. So this is where, this is say your column, and you have two cables here. The cables are applying a load of T on either side. So if you were to resolve it into two components, so you're gonna have one going vertically down for this particular load and the other component going horizontally. And for this load, you again have one of the component going vertically down and another going this way. Okay, now let's calculate what this angle is going to be. You know this length. So this is a triangle, right? This length, the purple length, vertical length is 5 meters. And all we have to do is get the angle. Oh, so you don't need it. The angle is given. This is 90 degrees. This is 30 degrees. Okay, so I can say this angle is 30 degrees. this angle is 30 degree. So can I say that, okay, let's look at the forces on this particular, can I say that the vertical component that you see, compressive component, is actually 2t cosine 30 degree. So this will be t sine 30 degree, t sine 30 degree, and over here you're going to see 2t sine, sorry, cosine 30 degree. Why 2? You have two compressive forces from both cables. So basically I'm interested in the compressive load, because it is this compressive load that is going to cause buckling of your column, and that is going to so what is column? Column is a long slender member under compressive load, and this is my compressive load here. So now I'm going to what I will do is, now I'm going to talk about a few things before I start. So that is, we're going to have to think about what type of column is this. This is a propped cantilever column. Why propped? See, it cannot move in. So if I consider this to be my, say, this is my y direction. So this is my z direction, and my x is going down like this. Oops. Z direction, and my x is going down like this. Okay. So so if I consider right now this little cross section, the cross section looks something like this. Y, and this is my z. That's how my cross section looks like. This is 40, and this is 100. Now you can see that because these forces are equal and opposite, there it cannot move in the this tip cannot move in the z direction, but is able to move in one direction, y. This is exactly what propped cantilever beam stands for, column stands for. So if I go back here, the propped one, this is totally cantilever column, means it's completely free at one end, and the propped one is here, propped. In the propped one, you cannot move, say for this one, you cannot move in these two direction, but it's able to move in this direction, right? Vertical direction, but not able to move in the lateral direction. So one of the direction is actually restrained, but the other one is not. That is called a propped cantilever beam, or you can say, I would say, cantilever column. Okay. Yeah, it should be a propped cantilever column, but a lot of the time if you search for it in the online, you're going to say that, see, they're talking about propped cantilever beam, but they actually mean column here. Okay, so this is the formula of interest, and you can see that effective length is 0.7 times L. So let me go back and write that thing down. So my critical load, so my critical load is equal to pi square E. I'm going to leave it as I right now. We're going to plug in the I later. 0.7 L square. That's the formula. Now, in which I you are going to write, it's based on whether you are writing about which direction you have the lowest moment of inertia. Now, if you see, the lowest moment of inertia will be about the y direction, right? In that way, your B, so your B is actually 100. This is your H actually, because you're taking moment of inertia about this axis, y axis. So this is your base. This is your base. and this is your height. So BH cube is going to be 40 cube divided by 12, and that gives me around 533.33 times 10 to the power. This is 10 to the power 3 millimeter to the power 4. If I write it in meter to the power 4, it will be 5.3333 times 10 to the power negative 7 meter to the power 4. Okay, now if I had taken it about the z-axis, then what would have been my value? It would have been this would have been my base, then this would have been my height, and my iz will be, you will see iz is greater than iy. So over here I'm going to put iy because it's going to bend about the y axis. Okay, so it's going to bend about the y axis where it has least moment of inertia. Now if I plug in the values, you can easily plug in the values now. So the modulus is 10 gigapascal, which is 10 times, so pi square 10 times 10 to the power 9. My iy is 5.3333 times 10 to the power negative 7. And now I'm going to say 0.7 times, the total length is 5 meter times 5 squared. If I do that, my critical load turns out to be 4297 Newton. That's my critical load. So so that critical load is nothing but equal to, so PCR is equal to 2t cosine 30 degree. So your T is going to be, you can easily calculate it, right? So you know that it's 4,279, and so that is the minimum critical load that you're going to be, sorry, that so 4,279 is the minimum critical load that you is the critical load that you have, and this is the tensile load that will cause some cause that critical load. So people, do you have any question regarding that?
Yeah, I have one. Could you please explain why you took the y direction as the minimum moment of inertia again?
Yes. I'm going over it. Anybody else with any other question? Okay. So
Professor, I got a different answer. I got 10 more than your answer.
10 more than my answer?
Yeah, I got 2,480.9.
It could be because I got 4,279 divided by 2 divided by cosine 30. My calculator gives me 2,478.5. Are you?
You're saying 79, but it's 97.
Oh, thank you. I'm calculating it as, okay, thank you, yeah. 2,480. It should be 80 people, oops.
Okay, thank you.
81 actually, it should go. Sorry. Okay, so
Yeah.
So your question was, why are we using
The y direction, moment of inertia in the y direction to be minimum, yes.
okay. Y direction b h cube. So in the y direction, your one is your b is 100, right? H
Yeah.
is 100. Is it not minimum in that direction? 5.3, 10 to the power negative 7. Okay, let's look at okay, people, here we actually have to, yeah, this is the minimum when you're considering it to be in the propped condition. In the propped condition, it cannot move in the z direction, it can move in the y direction. Okay, so if you're taking,
Yeah.
so if you were to take it about the z direction, okay, what would have happened? Your z direction is in this way. I will calculate actually the moment in the moment of inertia in the z direction in a moment, because this is not the end of the problem. But if you look at it carefully, so if I draw, say, any arbitrary cross section, say, okay, say this is, so this is your, so this is your y, this is your z, okay. So this is, say, we got it to be 140. All right, so if you look at it carefully, if you are considering about this axis, where is your base? This is your base. This is your B. Then this is your height. This is your H. So IY is equal to 100 times 40 cubed by 12. Okay. Whereas IZ, if you were to take it about this location, then this will become your B, this will become your height. So it's going to be what? 40 times 100 cube divided by 12. Which one will give you lowest value?
IY.
Okay. Now this is considering it to be propped one. Propped one means it's propped beam, meaning that it cannot move in the z direction, it is able to move in one direction. But if you consider it to be about the z axis, okay, then you can see that it can freely, so when you're considering taking moment about the y axis, it acts as a cantilever propped column, okay, because it is restrained by restrained in one direction, in the z direction, and it is able to actually so you can see that about the z. So if it is, okay, let me just say it, if it were to bend about the y-axis, so this is your y-axis, it is going to bend like this. Am I right?
Yeah.
About the y-axis. So that means it is actually bending in the z direction, which is kind of restrained by the two cables that you have. So we are treating it as a propped cantilever. But if you consider, for example, if you consider it to be, so this is your z-axis. So if you consider it to be actually bending it in this direction about the z-axis, okay, so it is actually bending in the y direction, which is the free direction. So that in that case, buckling about z-axis makes it act like a cantilever column. The reason why in this problem you have to consider both, because in one direction it is acting as a propped column, in the other direction it is acting as a cantilever column. But if you were to have any problem where, say, you do not have any problem with any restraint or anything, say if you have pinned or something, or pinned fixed column, then you have to consider which one, in which direction, in which moment of inertia is lowest. So about that moment, about the axis about which you have your lowest moment of inertia, or in that case you're gonna see bending in that direction. But in this problem you cannot say it, because we have to analyze it as two different columns. In the z direction it is acting as a propped column, in the y direction it is acting as a cantilever column. So I'm going to see what happens if we calculate it about the cantilever column. So my IZ is going to be, if you calculate 40 times 100 cubed divided by 12, you're going to end up getting 3.333 times 10 to the power 6 millimeter to the power 4. And if I convert it, yeah, I'm going to end up getting, so you can see that the value of IZ is 3.33 times 10 to the power minus 6, whereas for this one is 5.33 times 10 to the power minus 7. Definitely this is lower, but in this case we have to consider both axes. We cannot just take our decision based on about which axis you have least moment of inertia. We cannot take that decision based on that, because it is acting as different column in two different axes. So it is acting as propped cantilever when considering buckling about y-axis, whereas it is acting as a free cantilever column when considering buckling about z-axis. So if I go back to my lecture slide on cantilever, for cantilever beam column, it is, where is the cantilever? I want to show you guys here, cantilever. You can see that this is my formula, and it is going to be pi square EI divided by 2L square. So I'm going to actually, although your I is high, you have to keep in mind that your denominator is high as well. So you don't know which one will give you the lowest value. So I'm going, if I go back to my worksheet, so I'm gonna say, so I'm going to write it down like this. So now I know everything. I'll just plug in. Length is 5 squared. So that gives me something around, so you see you get 329, oops, 3290 Newton. So I'm getting a much lower value than this one. So if we know that obviously PCR is equal to 2t cosine 30 degree. So if you calculate your your value turns out to be something like, so you have two tension value. One is 2,481. One is 18,099. So obviously you're going to consider the lowest value, because it is going to, if you apply a load of if you apply critical load of 3,290, you're going to start seeing buckling about the z-axis. So this is your z-axis. So you're going to start seeing it buckle about the z-axis. Okay, so you before you, even if you apply anywhere around this, you're gonna start seeing it. You're gonna see buckling in this case both directions, but you're always gonna take the lowest value, because that is going to cause buckling first. So it buckles about the z-axis. So if you have any problem, say simply supported beam, a column or something like that, then you have to consider the where you do not have a column acting as two different types of column in considering the directions. Then you have to consider this, which one is lowest. But here, because it was acting as a propped column about the y-axis, but a free cantilever beam, cantilever column about the z-axis, we had to analyze both, because we do not know which one will give us the lowest value. And it seems like in this case, the lowest value is given by the cantilever column causing a buckling about z-axis. So any question? People?
No, we're good. I'm good.
No.
All right, so I will just do, I'm going to do one problem. This actually covers our column. You're going to see at best problems similar to this, nothing more difficult than that in your exam. Today we're going to look at something different as well. We're going to look at, I didn't post it, I will be posting it in your Blackboard, the combined loading and static failure theories. We're going to just touch upon it, because this is what you're going to be mostly, we're going to start off our machine elements class with this, you will see. I'm going to just give you guys an overview of it. This is, before I go over, we talked about Morse circle, we talked about stress transformation equations. Now it might have triggered your thought, like, why on earth do I have to go through this trouble to learn it? Well, basically, and if you remember beginning of this class, I said, hey, stress transformation is very important for your machine elements. Well, there's a reason, because stress transformation, you will see that it is widely used for analysis and design of members, structural members definitely, which are under combined loads. What do I mean by combined load? You may see something like this. Say you have a cantilever beam. So it is not only under a transverse load, you may see another load, axial load as well. So you have two types of load acting on it at the same time. Or you can see a torque applied on it too. So what do you have? So you have combined loading condition. So in order to analyze such structure, which is under three different types of loading condition, how do you analyze it? That's where this stress transformation comes handy. So you're going to, for structures which are under multiple loading conditions, you have to identify a critical point, say somewhere here maybe, okay? To identify a critical point, usually what people do is if they see failure on a structure again and again at the same location, that will be considered a critical location. If you do not know where your critical location for a structure is, then you will have to consider calculating the state of stress for several locations. What do I mean by state of stress? Say for this particular location, you're going to take a small element and you want to find out, hey, what's sigma x, y, what are the shear stresses, that state of stress. Once you know your state of stress for several locations, you can compare them, or if you know your critical location already, find out the state of stress at that location, and then you're going to draw the Morse circle. Once you know the Morse circle, for this particular location, say if this is the critical location, for this particular location, you're going to calculate relevant stresses such as principal stresses, maximum shear stresses. That will tell you, hey, what is the max? Not principal stress will give you the maximum normal stress at the critical location. And then you can use them in your failure theory to predict whether it's going to fail or not. So we're going to look at failure theory, but this is the main goal of our stress transformation. And I'm going to upload a problem as an example problem in Blackboard. I will let you guys, email you guys and let you and announce it as well. So you're going to look at there, you're going to see how I'm applying 3 different loading condition or 2 different loading condition and how you're calculating the principal stresses. And we're also going to look at another problem, a worksheet problem, that is our last worksheet problem, where you're going to see that how I'm using stress transformation in failure theory. Now let's look at failure theories. What are failure theories? Our ultimate goal, so far what you have studied beams, we have studied torsion, we've studied column. Our goal is always to predict whether the structure is going to fail or not. So in order, you studied all those so that you can actually understand, you are able to, you have sound knowledge on solid mechanics so that you can use that to apply that knowledge towards failure theories to predict failure. So in any 3-dimensional stress element, such as this one, so you can see that I have applied, I have normal stresses in the Y direction, in the X direction, as well as in the Z direction. Now, obviously, you have shear stresses in all planes, XY plane, XZ plane, YZ plane. So you basically, for a 3-dimensional stress element like this, so far, remember in stress transformation, we only studied plane stress condition. What is a plane stress condition, people? There is no stress in the Z direction, in the out of plane direction. That is it. So, but if you are talking about in reality, nothing is simple. Everything is complicated. So you may not see a plane stress condition. You may have some stress in the Z direction. If that is the case, then you will have 3 non-zero principal stresses. And this is how people actually arrange them. Sigma 1 greater than sigma 2 greater than sigma 3. And you're also going to have 3 shear stress components. Sorry, not shear, yeah. You're going to have 6 stress components. 3 are normal stresses and 3 are shear stresses. Will there be any shear stress in the principal direction, people? Can unmute yourself and tell me. Amir?
Yes.
Will there be any normal shear stress in the principal direction? I'm seeing in the chat.
No.
Jose said yes. Amir, what do you think?
I said no.
You said no. Well, I think Amir is right. There is no shear stress in the principal direction. Remember, in the principal direction, you only have normal stresses. If it's a 3D stress element, you'll have 3 non-zero principal stresses. And you're gonna have 6 stress components, out of which 3 will be normal and stress, 3 will be shear stress. Now, you will also have principal shear stresses. And this principal shear stresses doesn't mean principal direction. This just means your maximum shear stresses, okay? So you will see that if for this 3D, if you draw this Morse circle, you're gonna have 3 Morse circle. You can see that this is your sigma 1. This will give you your sigma 2. And this will give you your sigma 3. And for each of this, so one circle is made of sigma 1 and sigma 2. The other circle is made of sigma 2 and sigma 3. The bigger circle is made of sigma 1 and sigma 3. This is how it will look like. Now, principal shear stresses means just the maximum. I'm going to change this. I'm going to, when I will upload it, I will remove this. I don't want you guys to get confused. Okay, this is going to be maximum shear stresses. Okay, so for the AB circle, this is your maximum shear stress. Okay, so that's what I'm calling it. So how that is nothing but the radius of the AB circle. What is the radius of AB circle? Sigma 1 minus sigma 2 divided by 2. And that is my tau 1/2. Now for the BC circle, okay, for the BC circle, this is my, let's talk about AC circle. Okay, BC circle. This is my, for the BC circle, this is my radius. My radius is sigma 2 divided by sigma 3 sigma 2 minus sigma 3 divided by 2. So that gives me this shear stress for this circle. And for the big circle, my radius is sigma 1 minus sigma 3 divided by 2, and that's over here, tau 1/3. So definitely whichever, right now, based on this figure, it seems like tau 1/3 is maximum. But if you'll have to calculate all 3 and find out which circle gives you the maximum radius, and that will be the absolute maximum shear stress. And remember the in-plane shear stress, maximum in-plane shear stress we talked about. Maximum in-plane shear stress is where you're going to draw the Morse circle with sigma only with sigma x, y, sigma x, sigma y, and tau xy. With that, that is called the maximum in-plane shear stress. That is only for plane stress condition. Now I'm going to, this is the most generalized condition. If I draw it for the plane stress condition, remember for the plane stress, sigma z is not there, is equal to 0. I don't have any sigma z. I only have, what do I have? Sigma x, sigma y, tau xy, that's all I have. That's why it is called a plane stress condition. And this is what you have been studying in the previous classes. We talked about, we didn't look at the 3D generalized condition, but things get complicated. Now we are starting to introduce slowly these complicated things. But we looked at plane stress condition where your sigma z is 0. Under that circumstances, if you draw your Morse circle, you will see that your sigma 3, so this is your sigma 1, this is your sigma 2, your sigma 3 is 0. Why? So you can see that sigma 3 is 0 because the normal stress in the z direction is 0. So this, if it is non-zero, then you have a sigma z, and you can see that definitely over here, this point is not at the origin. Whereas over here, this point is at the origin, okay? That's because sigma z is 0 here, okay? Now, you still get 3 more circle. In so far, everything you studied is with this more circle. Okay, we only looked at this more circle. We didn't look at in a more broader spectrum, considering all 3 axes. But here, now we're gonna start looking at it. So you're gonna, but I did touch upon a little bit about, so this is whatever shear stress you see, that's the maximum in-plane shear stress. And that's equal to what? Sigma 1 minus this radius, this pink circle radius, which is sigma 1 minus sigma 2 divided by 2. Okay, and for this, this black circle that I have, the radius is going to be sigma 2 divided by 2. And for this purple green circle, your radius is going to be sigma 1 divided by 2, because sigma 3 is 0. So basically, these are the 3 radii we have. Whichever gives you the max value, that will give you the absolute maximum shear stress. So we're talking about absolute. But this one is your maximum in-plane shear stress. In-plane, because this is the circle which has which considers all the normal stresses, X and Y stresses, maximum in-plane shear stress. Okay, so let's look at theories. So why are we looking at all these? These are important because we want to look at theories of failure. We need to be able to predict failure, and there are many types, many theories to use. We're going to look at, basically it is divided into 2 groups. One group is failure criteria for brittle material. The other is the failure criteria for ductile material. For brittle material, if you remember from my ETM 2171 class, when we had stress versus strain, for brittle material, you will see it goes straight up and snaps. You do not see any yield point. For a ductile material, is going to go up like this and fall, snap somewhere here. So this is your ultimate tensile strength, and somewhere here you're going to see your yielding strength. Okay, and for brittle material, we consider it to have failed if it has reached its yielding point. Why? Because it has, after yielding point, it starts to deform plastically, and you don't want to have any equipment that is permanently deformed. And for brittle material, this is where we're going to consider failure criteria, failure, and that means it has failed. It exhibits rupture, that means total fracture. But for ductile, it is exhibiting yielding for failure. So we're going to look at here some failure criteria for brittle material first. Okay, one of the failure criteria theory, failure theory, is the maximum normal stress theory. What does this theory tell you? It tells us that failure occurs when the largest principal stress exceeds the ultimate stress, either compressive or yielding, compressive or tensile. So we're saying that, hey, remember I talked to you about a structure under different types of loading, and I told you, hey, this is the critical location, calculate the principal stresses. So if this were to be made of a brittle material, so after calculating your principal stresses, you're going to compare it. If you are using this theory, no maximum normal stress theory, you're going to compare it with its ultimate tensile or compressive stresses. And if it is larger, then we're going to say, hey, it will fail. So this theory is predominantly for brittle materials that have same strength in tension and compression. We're saying that, hey, if its ultimate, its tensile strength is, say, 30 megapascal in tension and minus 30 megapascal in compression. That means the value, the magnitude of the strength values in tension, of the strength in tension and compression are same. Now, so remember, always keep in mind, this is what you will follow. Sigma 1 is always considered greater than sigma 2. Sigma 2 is always greater than sigma 3. Now, based on this failure criteria, I'm going to say, hey, failure will occur if the first principal stress is greater than the ultimate tensile strength, or if sigma 3 is the lowest one, okay? So, or sigma 3 is less than or equal to minus sigma UC. UC is the compressive strength. So if I draw a graph of, say, stress versus strain over here, sorry, not stress versus strain, stresses, okay? I'm going to say draw, so this is sigma, say, so you are considering two principal stresses. So I'm going to say these are the stresses on the body. So I'm going, this is your ultimate tensile strength value. This is your ultimate compressive strength value. Similarly, in the y-axis, ultimate tensile strength, ultimate compressive strength. And if I draw a nice rectangle, oh, sorry, a square, because it has the same values, then the non-failure region will be everything inside this square. That's my non-failure region. That means if you have a combination of principal stresses, say my sigma 1 is somewhere here, and say my sigma 3 is somewhere here, or you can say, oops, I'm sorry. So, or you can say sigma 3 is somewhere here. This is sigma 1, and so sigma 3 is somewhere here. For a combination of principal stresses that falls within this boundary, we're going to say that it's not going to fail. What if you have some principal stress, say, somewhere here? Say you have sigma 1 here and sigma 3 somewhere here. It falls outside the range. Then we will say it will fail. So, so that is one of the failure criteria we have. So if points corresponding to principal stresses fall within the square boundary, then the material will not fail. So that is one of the criteria, maximum normal stress criteria. There's another criteria called brittle column mode theory. This is another theory that you can use. What is done using in this theory? You're going to find out this is usually used for brittle materials which have different ultimate tensile stress and ultimate compressive stress. Say the ultimate tensile stress is 30 megapascal, but the ultimate compressive stress is, say, minus 10 megapascal. So the magnitude is different. And what do you do in this case? In this case, you're going to draw what is called Mohr circle. You're going to draw Mohr circle. So x-axis has normal stress, y-axis has shear stress. So you're going to draw a Mohr circle considering the ultimate tensile ultimate compressive stress and 0. So this is going to be your ultimate compressive stress. So sigma ULTC. Okay. So your Mohr circle radius is going to be somewhere in between. So the radius value is going to be sigma ultimate tensile compressive strength divided by 2. That will give you the radius. Okay. And then in the middle, you're going to have the center. And if you draw, this is how the Mohr circle, only considering the ultimate compressive stress, will look like. You'll do the same thing for ultimate tensile stress. So this is your ultimate tensile strength, sigma ULT T. Okay. And for this little circle, your radius is going to be sigma ULT T divided by 2. And this is where the center in the middle. Okay, both are going to be at the origin, touch at the origin. Now you're going to draw a line that is tangent to both the circle. The envelope that you have created, this envelope is your non-failure region. So failure envelope consists of two lines tangent to the Morse circle for ultimate tensile and compressive stress. Material will not fail if the Morse circle of the given state of stress falls entirely within this boundary. That means for a case like this, remember for this case, you're going to find, hey, you're going to draw a Morse circle. For this particular case, you're going to draw a Morse circle. So if your Morse circle, say, is something like this, say your Morse circle looks something like this. So your this purple circle falls within this yellow envelope that I have, shaded envelope that I have created. Then we will say, hey, that structure will not fail. If you end up having some circle like this, say, if you have a green circle where it is falling outside that shaded region, then we are going to say, hey, it will fail. So this is exactly what it says. It will not fail if the Morse circle of the given state of stress falls entirely within the boundary. All right, so I have, this is for, you can also check the brittle Coulomb mode theory. Either you can do it using this, drawing the Morse circle, which we'll look into it later on next class, or you can use, if you have the problem as a plane stress state. Remember, for plane stress, one of these principal stresses will be 0. Okay, so if you have plane stress condition, you can also calculate the factor of safety. If it is greater than 1, then it will not fail. So N is your factor of safety. So I'm going to start this next class, and we're going to finish it next class, some of the failure criteria. But mainly next class, we'll talk about your final exam. And we'll look into one problem related to failure theory. And I will post a few example problems related to failure theory, and that will be it for the failure theories. Any question before I end the class, people?
Professor?
Yes.
When is our finals next week? It's Thursday, you said, right?
Yeah, it's on your, so last class, I think I mentioned it. I'm going to also send out an email notification when the final exam going to be. It's on your syllabus.
All right.
Go to your syllabus. I'm opening it just to let you guys know before you leave.
Thanks.
Okay, based on the syllabus, your exam is on the 14th. So that's Thursday, 14th, but it's not at 4 p.m. It's at 3 p.m. people. Okay.
Yeah.
All right.
The duration of that is how long for the final?
Yeah.
So that's what I will talk about on Thursday, but your final exam is going to be an hour and a half, and then another half an hour for scanning and uploading the documents.
And it will start at 4 p.m. or 3 p.m.
It is 3 p.m. Based on the university's schedule, it's 3 p.m.
So we have till 5 p.m. to submit the final to you.
Well, okay, here's the thing. So it's going to be either an hour 15 minutes or an hour 30 minutes, okay? So I will be on, it's just going to be like previous one. I'm going to be on Zoom. You guys are going to take your exam and finish it. But the remaining 30 minutes that I'm giving, you will be actually scanning and uploading. You will not be working on your problem. Does that make sense?
Absolutely, yeah. Thank you.
Okay. Yes, and I do, um, um, we are all professionals here, and I do believe that you guys will follow that instruction, except for those who have time extension, definitely. Okay, I'm going to talk more about your midterm final exam on Thursday, like what to look into, what chapters are more important, and what chapters I already mentioned to you guys, like for the first, everything before for until the first midterm. I'm not gonna explicitly test you on it, but you will need those concepts for the remaining topics. And I will also send out an email as well on Thursday so that we are all on the same page.
Yeah.
All right. Cool. Anything else?
Is this the last topic that you were
This is
in
the last.
the final?
This is the last topic. And for this last,
Okay, thank you.
I only look at the example problem that I will give, I will post, and the worksheet problem that we will solve. That's it. You don't have to go too much in detail. Any problem, if you are asked, will be very similar to what the problem I have posted or I have solved in the class. Same goes for your column.
Thank you, Professor.
Okay. All right, people. I'll see you all on Thursday. Don't miss the class
Thank you,
on
Professor.
Thursday.
Appreciate it.
Very-
Thank
Okay.
you.